Hello everyone. In this video we will be looking into the applications of syntax directed translations. So this syntax directed translation is a kind of technique that we had learned till now in the previous sections using the syntax directed definition, right? The actual implementation happens using syntax directed translation techniques. So this syntax directed translation is used for type checking and intermediate code generation. As we know, in the phases of compiler, the phases of compiler is divided into front end and back end. Alright, to the front end, the input that is given is the string or the programming language or a statement. Let me take it to be a sentence. Okay. So this programming language or a input string or a sentence is given as input to the front end, where front end has three phases. The first one is lexical analyzer, second one is syntax analyzer, and the third one is semantic analyzer. Alright, so lexical analyzer takes the input string, divides it into tokens, sends to syntax analyzer. Syntax analyzer, using the context free grammar, produces parse tree. This parse tree is checked in semantic analyzer whether it is semantically correct and produces annotated parse tree. Okay, so this is represented using syntax directed translation, which in turn produces syntax tree. Alright. Syntax trees are used for type checking and also for intermediate code generation. Alright, so this syntax tree is given as input to the back end now. Back end has other phases such as code optimizer, intermediate code generator and all that. Okay, so this code back end in turn produces the target code which is needed. So this whole part forms the compiler, and these are the phases. So over here now we have reached the last phase of the front end, okay, the semantic analysis phase. Over here we get the syntax tree that is being generated using syntax directed translation techniques, which is used for type checking and intermediate code generation. So this intermediate code which is generated by the front end is given as input to back end. Intermediate code generation is represented using syntax tree. Alright, that is the reason why we need to learn about constructing this syntax tree. Okay, so there is a difference between syntax tree and parse tree, which we generally don't observe. A parse tree, till now what we had obtained is a hierarchical structure, okay, that is used to for the derivation of grammar to obtain input string. Hierarchical structure that represents the derivation of grammar, okay, to obtain the input string. So it has all the productions of the grammar to get the input string. That is represented using parse tree. Whereas syntax tree is a kind of hierarchical tree that represents the syntax of the programming language. Okay, for example, if this is the programming language and that is represented using the syntax tree in this form. Alright, it has all the syntaxes of the programming language as well as the input string. Okay, so this is the difference between a syntax tree and a parse tree. So now using this annotated parse tree, we are going to construct syntax tree. Okay, so we will be using two types of syntax directed definitions over here for construction of parse trees. The first one is S attributed definition SDD and L attributed definition SDD. S attributed definition SDD is used for construction of syntax tree that uses bottom up parsing method. Alright, whereas L attributed SDD is used for construction of syntax trees that uses top down parsing method. Top down parsing method. So this is the difference between syntax directed definition and syntax directed L attributed definition and S attributed definition and L attributed definition. Okay, so using these two types of definitions, we will be constructing the syntax tree depending upon what type of parsing method is being used, whether it is a bottom-up parsing method or top-down parsing method. Alright, the syntax tree has nodes, right? Syntax tree is represented using nodes, and these nodes, okay, these nodes are represented in the form of a construct, or I can say each node in a syntax tree represents a construct. Okay, so and this, if this is a node, this node has various children. Let me say C1, C2, C3 to be the children of this node. Alright, so the children of the node of this node represents the meaningful components of the construct. Okay, this is constructed or represented only when we look into its children's component constructs. Alright, so now I told you that syntax tree is represented using nodes. Okay, so we will see how the nodes of the syntax tree are represented now. The nodes of the syntax tree are represented in the form of objects. So that will be implemented, not represented, sorry. The nodes in the syntax tree will be implemented in the form of objects. Okay, will be implemented in the form of objects with a suitable number of fields. This object will have many number of fields. The first field being OP. OP is the first field, which is the label of the node. Okay, for this node it is the label, the first field, and the other fields which is there for this object, okay, depends upon what kind of node it is. So if a node is a leaf node, for example, over here we see this syntax tree, and these are the nodes over here, A, C, C. This is 4, I'm sorry, for this example. So these are nodes, I mean leaves. Okay, these are also nodes, but it is the leaf. That node is a leaf. This is one leaf, leaf, leaf. 3 leaves are there. So if the node represents leaves of the syntax tree, then the construction function to create that object. Now we have to see how to do that. If it is a leaf, then the construction function will be represented in this way. Leaf of in the arguments we will pass OP, which is the first field, followed by another field which is called val. Alright, it is an additional field that holds the lexical value for the leaf. Always the leaves of the syntax tree are nothing but the terminals. Okay, so they will hold the lexical value of the leaf, which is being sent by the lexical analyzer. Okay, so using this construction function, the leaf object will be created. Alright, so if there is a node object, okay, let me write this to be interior node. Okay, other than leaves, whatever nodes are there, they are nothing but interior nodes. So those interior nodes object can be created using this constructor function, which is node of OP. OP is the first field, followed by the number of children that it has. This node has up to ck. If it has k number of children, the additional field holds the value, okay, for these children, attribute values for these children. So for this example, there are 3 children for this node. So for that, the node object created using the construction function is like this: C1, C2, C3. Alright, so these are 2 types of objects that is present in a syntax tree. Alright, depending upon what kind of node it is, we create the object. To create the object, we will be using these two constructor functions. Alright. So let us take an example for constructing syntax tree for a simple arithmetic expression. So this simple arithmetic expression contains only two binary operators, that is plus and minus. Okay. So these two operators, this simple arithmetic expression which is there, follows the same precedence level. These two operators follow the same precedence level. They have the same precedence level and they are left associative. That means the computation happens from left to right. So if this is an example, I take this as an example. So how is the computations happening? Always what we do is we calculate what is the value of a minus 4, and that value in turn is sent to C to add. Okay, a minus 4 is computed and that value is added with C. So that is the meaning of left associativity. Alright, so all the non-terminals have one synthesized attribute called node. Okay, these non-terminals have one synthesized attribute called node, which represents a node of the syntax tree. So let me write the nodes over here. As I told, it has only one synthesized attribute called node, which represents the node of the syntax tree. So this expression can be an identifier or a number. So that is the reason why I have used these two productions in the grammar. Okay. So to add, I have add and subtract, I have used these two productions. Okay, this is the type of grammar we write, okay, using these many productions for computing simple arithmetic expression. So for this productions for the grammar, let me write the semantic rule. This in turn forms a syntax directed definition. So beginning with, I told you it is a synthesized attribute which is called node, which is equal to, these are leaves, right? These are leaves, correct? Leaves are nothing but the terminals in the production. So since they are terminals, they are nothing but leaves. So what is it having? The value semantic rule that we define as a new, it creates an object using the constructor function called new leaf, having the OP field called num, because it is a label. Okay, label of the field called num, followed by the attribute. Okay, attribute value. So what is the value I have sent? Num dot val is the attribute value, that is the lexical value that is been sent by the lexical analyzer. In the same way, I write t dot node is equal to new leaf, it is id. Okay, id is the OP field, comma id dot, for this let me send the lexical attribute value to be entry. Okay, so these are the semantic rules for these two productions. So I told you that it uses only synthesized attribute. So t dot node will be equal to e dot node for this production, and for this production e dot node will be equal to t dot node. The value of t dot node will be sent to e dot node. Now observe over here, n e dot node will be equal to, they are interior nodes, right? So interior nodes attribute value or the object value for that node is computed using the constructor function called new node of, what is the OP field that is being used? The label. We are subtracting these two values. So that will be minus, which is represented in single quotes, comma e1 dot node, attribute value for its children. So e1 and t are the children. So e1 dot node, comma t dot node. Alright, so this is the semantic rule for this production. In the same way, I write the semantic rule for this production in this like this. New node. Now the OP field, operator field it is plus, comma, E1 dot node, comma, T dot node. So this is the way of writing the semantic rules for the production in our grammar, which computes simple arithmetic expression. Okay, so using this syntax directed definition, we will be drawing syntax tree. I have taken this as an example to construct the syntax tree. Okay, A minus 4 plus C. As we had seen, each node is represented in the form of object. All are nodes in the syntax tree, which is represented in this way. So each node is represented in the form of an object. So object has various fields, the first one being the OP field. So let me draw that to be plus for this node, followed by additional fields. Okay, so additional field is for this operator, okay, and for this ID, right? Over here A is an ID, 4 is a number, C is an ID. Alright, so for this ID I have created this field, and for this operator I have created this field for this object. Okay, so then this also is represented in the form of an object, this node, which has first field which is minus, followed by two additional fields to hold its two children's value, attribute value. So this also is a leaf of the Parse tree, which has ID as the OP field, followed by the label for that value, label of the value. So what is it? It is the to enter the entry for this A, this identifier A. So that is stored over here, and this num also is represented in a form of an object where the first field is num followed by 4. Okay, so 4 is the token that is being sent. Alright, so the field that is there for this object has two additional fields, that is pointing for this field is pointing for this child, and this field is pointing for the other child. Alright, in the same way, this field in for this object of the node is pointing to this child, whereas this second field is pointing to this child. This in turn also has two fields because it is also represented in the form of an object. So the first field is ID, and this is to entry for the identifier C. Alright, so that is the way we represent the syntax tree. Okay, so the solid lines which I have drawn, these are the edges in the syntax tree. Okay, so now we have to also write or draw corresponding parse tree for this syntax tree, which is represented using dotted lines. Okay, what does this parse tree contain? It is a hierarchical structure of the non-terminals or the nodes, that is derivations of the grammar that is there. That also is represented to get the desired input string. So that is the parse tree. So let us draw parse tree, which is represented using dotted lines. Okay, to get this input string we have used this grammar, right? Let us draw these derivations over here. The first one being E. E in turn produces E plus T. This E in turn produces E minus T. Okay, so this in turn produces T, which in turn produces ID. So this is the way we write the parse tree, right? and this T produces num. I am using these derivations, these productions, alright. Okay, next for this T also I write ID. Okay, this ID is A, this num is 4 and this ID is C. So this is a parse tree for this syntax tree. Now let us draw syntax tree nodes which is represented using dashed lines. Okay, what does this node represent? Each node represents, or it is represented in the form of an object. So what is the object corresponding to this node, that we will see. Okay, so this dashed line represents the syntax tree nodes which points to this object, correct? Because I am taking the value of ID. Okay, so this also points to this object, right? Because the ID value is sent to T and the attribute value of T, and this value is in turn sent to E. That is the reason why these two nodes are pointing to this object. Alright. In the same way, this node is pointing to this object because it has the value of this as well as this, ID minus num. That value is stored in this object. That represents this node or non-terminal, correct? What is this pointing to? E minus T, right? Which is stored in this object. Okay. So it is pointing using dash line, syntax tree node. Okay. And what is T pointing to? T is pointing to num. Right? See, over here it is pointing to num, or it produces this object. So I will be using through the dash lines, I will be pointing it over here. Also, what is left? This T is left. T, this dash line represents syntax tree node which is pointing to this ID, this object. Okay. In the same way, what is this object having? It has the value of this what? ID minus 4 plus ID. Okay. A minus 4 plus C. That value is stored in this object. So that is being represented for this node, right? I mean for this non-terminal E. It is pointing to this object. So this is how we represent a syntax tree, okay, for this expression A minus 4 plus C. So what are the steps for construction of this syntax tree? Over here, the first step that I take, okay, that I write, let me write it as in the form of P, okay. So first production is I construct the leaf node, right? First object that is been created. New leaf of ID comma entry for A. This is for P1. Whereas for P2, it is for this new leaf of num comma 4. What is P3? P3 now is this object. Okay, what it is an interior node. So that is represented using this constructor function for this object. New node minus first OP field comma the first additional field, okay, entry for first additional field which is P1, this object, right? So I write P1 for this comma P2 for this one. Alright, next the fourth production over here is for this number, identifier. So it is a leaf, right? So the constructor function that I have used is new leaf ID and field to enter C. And what is P5 now? P5 is this one. Okay. This is P1, P2, P3, P4. This is P5. P5 is an interior node. For that, the constructor function is new node of plus comma P3 comma P4. Okay, so these are the steps for construction of syntax tree for A minus 4 plus C for this input string. So when asked in the exam, you need to write these two things. Okay, you have to draw this syntax tree and the parse tree and the nodes. Okay, syntax tree nodes that is been represented. How it is represented also you need to write. Okay, so nodes are over here. Basically, first thing what you need to understand is the nodes, okay, are represented in the form of records. Okay, these nodes are represented in the form of records. The object that is there, the additional field that is there for this object is represented in the form of records. Okay, it might have a pointer over here which is pointing to the additional field that is there for its child. Okay, second thing is syntax tree edges. It is represented in the form of solid lines. The parse tree is represented in the form of dotted lines, whereas syntax tree is represented in the form of dashed lines. Okay, using this we need to write the nodes. Okay, how the steps are represented for construction of this syntax tree. That also you need to write. So I hope it is clear. Thank you.